All right, in this work example, we're going to be looking at some vectors and scalars and some of the first quantities that were introduced to distance, displacement, speed, velocity. So it says a girl runs 120 meters due north in 15 seconds. They've given us a nice little compass rose here. So north is this way. And I'll draw a little vector like that and label this as a displacement of 120 meters. And I'll also put the time that it took, 15 seconds. I like to keep track of it like that. It then says she went due east. So I'll make this one a little bit shorter as it's only 80 meters. And so here's sort of like the second leg of the trip, 80 meters. And so you can see what I'm looking at. Let me do this to anticipate perhaps your question there. Thank you. The time is 12 seconds for that. So 120 meters due north in 15 seconds, turning right, going 80 meters in a time of 12 seconds. It says, draw and label for resultant displacement R. So if you remember that displacement is defined as the net change in position. It's from start to end. What do you think the solution to this is going to look like? What am I going to draw here? Who can show me with like an arm vector in the class? There you go. It's going to be this guy right here. And here's the general rule, because you remember you have a learning objective. Let's remind ourselves what that's all about. You have a learning objective to use vector addition to add two or more vectors. Exactly what we're doing here. So we're adding this displacement to this displacement. And the rule for adding two vectors in general is this: place the vectors head to tail and draw a line connecting the tail of the first vector to the head of the last vector. Okay, if you're only adding two, it's just, you know, the tail of the first vector to the head of the second vector, connecting those dots, that's your resultant R. Resultant is just the sum, right, of the vector addition. Or it could be subtraction. Subtraction is just adding a negative. It's like you learn in math. A negative vector just means it's pointing the opposite way. It's like the negative of east is west. Okay, the negative of north is south. All right, so in general, the rule to add vectors, I'll say it again, is that you place the vectors head to tail. So like there's the head of the first vector, and I place the tail of the second vector at the head of that. All right, so I've placed them head to tail, and I've connected the tail of the first vector to the head of the last vector. So that's my resultant displacement. Some of you might even have a way in mind to calculate what that is. Okay. So the question goes on to ask us to calculate the speed of the girl, her velocity, and the direction of the velocity with respect to the initial task. So let's do that one at a time. If you rely on your definitions that we got down from yesterday, and remember, that's part of the learning objectives too, define speed, displacement, velocity, right? Those are three of them. We defined, I think, 4 terms yesterday. So what is speed? It's the total distance divided by the total time. And that's readily calculable. So hopefully you're good with 200 meters per 27 seconds. Any questions about where those values came from for calculating the speed? Everybody connect that pretty well. It's like, yeah, that makes sense to me. Got it. That's the definition. Like, wait, where'd you get 200 from? And they have that question. So if you go 120 this way and 80 that way, see what I've done there? Just added those. Right? That's the total distance, right? Total distance is 200 meters. Thank you. And the total time, likewise, is just if it took 15 seconds and then 12 seconds, then the total time was 27 seconds. Do not report your speed like this. The speed is 227 meters per second. You know, that's like, oh, I forgot my calculator. You know, take the ratio, class. Come on, you get decimal approximation there. So what would you report the answer as on this line down here? calculate the speed. So what would you put down? In the units, they sort of give you a clue, meters per second. So what would you write down? Call it out if you know it. Or get your calculator out if you need to. .4 would be what I would round that to. Okay, your calculator might show 7.407407 repeating. 7.4, 2 significant digits, the first decimal point. That's a good answer for the average speed. Okay, and it comes from this calculation. The question goes on. You can read down here to say, calculate for the girl the magnitude of the average velocity v and its angle with respect to the direction of the initial path. All right. So let me kind of here with it. Let me get rid of this speed calculation. It's still up there if you need it. In fact, it kind of belongs up there, right? All right, so if we're going to get the velocity, we need to know what is velocity. How do we define it? Does anybody know the definition of velocity? Anybody keep good notes from yesterday? It's not the same as speed, right? This question started with categorizing quantities as either vector or scalar. That's a clue, right? That's saying, hey, I did that for a reason because now I got to remember that speed is a scalar defined this way. Velocity is a vector defined differently. What is the definition of velocity? We can't just use it interchangeably with speed anymore, like it's done sort of in popular culture, right? As a student of physics, we got to appreciate that slight difference between a scalar and a vector quantity because we're going to get different answers here. All right, and so let's remind ourselves that velocity is the displacement over time. Okay, we use S for displacement, so we can kind of say like this was the first displacement, this was the second one. Whatever kind of notation helps you keep track of like S sub 1, S sub 2, whatever. Now we're going to add these and get a resultant. How do we add these vectors? Does anybody know? If I were to write this, does that give you a clue and help you go, oh, I see what you've done there? Or is that like, whoa, you put a radical up there, you got exponents. What are you doing there? So I've taken Pythagoras' theorem, a squared plus b squared equals c squared, but in this case, c is r, the resultant. And I've just taken the square root of both sides, right? So I just used Pythagoras' theorem to try to solve for this. And I skipped a bunch of steps like they tell you not to do in that stuff. If you're comfortable going to this step right away, go for it. You might even just plug it all in your calculator. Like take the square of that, add the square of that, take the square root of it. Who's got the answer? I strongly encourage you, even if you don't have like a good scientific calculator with you today, just use your phone. It's got a good calculator on it. Practice the calculation, make sure you're getting the same answer everybody else is, and then make a note to yourself, bring scientific calculator to physics class. Every day. You'll need it. We don't want to have to do this in our head. Like, oh, let's do a little bit of mental math here. Let's see, square of 120. Call it out when you got it. 80 squared is, so check it again, 80 is incorrect. We gotta do 80 squared plus 120 squared and then take the square root. 144.2, and there's more, right? So maybe that's okay, like just leave it like that for now. Because remember, that's not a final answer. We're not reporting that as anything. That's just the displacement. So in order to get the magnitude of velocity, what do I gotta do? I say I calculate the displacement using Pythagoras' theorem. And it still took how long? 27 seconds, right? That didn't change. It took 27 seconds to get from here to here. That's the net change in position, right? From starting point to end point. That's what displacement is. But she still had to run like this, 200 meters. So her speed was 7.4. Remember, we got 7.4 meters per second for this. But what is her velocity? So this is the correct displacement. And even if you didn't get that calculation, trust that it's correct and calculate the velocity with us. 144.2 divided by 27 is slower than the speed. And it might bother you that it's like, wait a minute, you're telling me for the same motion, her speed is this, but her velocity is less. And that's because of the precisely defined way that we have these quantities, sort of spelled out, right? That velocity is displacement per time, and the displacement is different than the distance. And so we just have to appreciate that. Sometimes we care about the speed, sometimes we care about the velocity. Whatever they ask us to calculate, we can do it. We have those definitions for a reason. And you will be able to rely on open notes for at least the first couple of weeks of these quizzes. But I challenge you is like, okay, that's not too bad. I kind of know distance per time, miles per hour, like I guess. The angle's a bit tougher. Okay, now before we charge on ahead to that, I want to be mindful to field anybody's question that's like, wait a minute, can you show us this a little bit more? Like what are we doing here? Anybody have any clarifying questions on that? So it's just the geometry of Pythagoras, or if you have a right triangle, right, then this side is the hypotenuse, and they usually call them A, B, and C. And we say A squared plus B squared will equal C squared. Right, and so we have a right triangle because we went due north and then due east, and so we know that's the right angle there. So we're solving for this hypotenuse using Pythagoras' theorem. A squared, 80 squared, right, that's the distance. B squared, 120 squared, equals R squared. And then to solve for R, we just take the square root of both sides, right? So R is equal to the square root of all of that. And then just type it in your calculator, 120 squared, and follow order of operations, right? Like 120 squared plus 80 squared gives you a certain number, and take the square root of it. 120 squared is 14,400. 80 squared is 6,400. The sum of those two is 20,800. And so R squared is equal to 20,800. And so R is the square root of that, which is 144.2. And then once you have the displacement, you can calculate the velocity, because velocity is displacement divided by time. That's this. The angle here, we'll call it theta, is calculable. We know everything about this right triangle. We know this distance, we know this distance, and we know this is now 144.2. Whatever your favorite trig function is, you can use it to solve for it. So Socatella, yet another mnemonic device, helps us remember our trig functions. Hopefully this isn't the first time you've heard this. If it is, no worries, we'll get you caught up to speed here. Does anybody have a favorite trig function? Mine's the tangent. I like the tangent. But some people like the cosine, other people, they're partial to the sine. But, for a question like this, it's whatever your favorite is, right? We know everything. We know all the sides. Sometimes you're forced to use one of them. You don't know the hypotenuse. Like initially we didn't know the hypotenuse, right? And because we calculated the hypotenuse, it's my suggestion to you to use the function that relates the sides that were given. And so let's remind ourselves what this is all about. This Socatella is a way to remember that the sine of some angle theta is equal to a ratio of sides, the opposite over the hypotenuse. So like here is the angle theta we're concerned with. They ask us what is the angle with respect to the direction of the initial path. Well, that's the initial path, right? Due north. So I want to know this angle here. With respect to due north, what angle is this that put our student, that put the person over here? So the sine of this angle is equal to 80 over 144, right? Just a ratio of those sides. This is some function of an angle that's equal to this ratio of sides. Likewise, the cosine of that angle would be adjacent. So this is the side adjacent to the angle. I'll use values for this now. It would be equal to that. The cosine of the angle would be equal to that. And the tangent of that angle would be equal to opposite over adjacent, right? Opposite over adjacent. So opposite, adjacent. Now we want to know the angle. Because we know all the sides, we could use any function to solve it. Here's how you do it. Use the inverse tangent. Sorry. The inverse tangent of the ratio of sides solves for the angle. So this is why I strongly encourage you to bring your scientific calculator with you to class. You need to find that button on your calculator. Everybody's calculator is a bit different. But you can use your phone calculator, take the inverse tangent of 80 over 120, or take the ratio 80 over 120, and then take the inverse tangent of it, and that solves for the angle. If we made a mistake calculating this, then that mistake would show up if we use the sine or the cosine, right? Which is why I suggest use the given information, okay? So that your mistake won't, hurt you there. Does anybody with a calculator have the bravery to offer the answer? 33.7, anybody else get anything different or want to round it slightly differently? 33.7, I think, is a good answer that would earn full marks. I would suggest to round it to 34. So this angle here is 34 degrees. Prove it to yourself that the cosine would work too. You got your calculator out already? Why not? It should be true that the inverse cosine of 120 over 144.2 or whatever gives you the same answer, right? So the cosine of those ratios, or the inverse cosine of that ratio, would be equal to the inverse tangent of this ratio. And if you really, just for completion's sake, want to do it, it should be also true that the inverse sine of opposite over hypotenuse, right? That should also give you the same 34-degree angle, right? So that's why I said use your favorite trig function, right? Like, I don't like the tangent. I don't like tan. I like the sine, whatever. Use your favorite one. It's only my suggestion that for this calculation, you use the tangent. And again, for the reasoning of if there's a mistake here, that mistake is going to propagate into your final sort of answer there. But that's the correct solution, 34 degrees. Because velocity is a vector, we want to know both the magnitude and the direction, right? Like, that's the way we report the direction of a vector. Oh, it's going 34 degrees east of due north. Like, if you're a pilot and you're saying, hey, what heading do I take in order to arrive at this airport? Oh, you need to go 34 degrees east of due north. Pilots oftentimes have to correct because there's wind vectors. Like, if a pilot just goes in a direction without regard to what the wind is doing, the wind will blow them off course. As I said, oh, because I have a wind heading of it's blowing me due east, I need to put my plane a little bit more west to correct for that. So I actually end up where I want to go. There's very practical utility in this physics. Okay, it's very practically useful. All right. This has been another work example with Dr. Schleif. We'll see you next time.